tau 2, that's 2 to the power x. Now claim let A be a subset of x. Now A is compact if and only if A is finite. Now we already know the if part. If A is finite, then it's compact. Okay? This part, the if part, the right hand implying the left hand statement, already done. For this part, now assume that A is compact. Now we already have a clue how to prove that then A is finite. Well, we actually need to produce a particular open covering of A. If A is not finite, infinite, such that any subcovering of that will not do. What will that be? Just the singletons which comprise the set X. Now, well, let's proceed by contradiction. Suppose A is infinite. This should lead to a contradiction. Now, G consisting of singletons X, X in A, we have seen that this is an open covering of A. Is an open covering of A. It's indexed over cap A. Now, does there exist any non-empty finite subset of cap A such that when I take that finite subcollection of G, which will also cover A, now take any finite non-empty subset E of A. But then, let me continue here. Is this a finite subcovering? No. Well, taking any non-empty subset E of A, that corresponds taking any non-empty finite subcollection of G, since A here is the index set, is not a finite subcover of G for A, since if I take the union of x's, x in E, this will be just E itself, and this does not contain A, since this is finite while this is infinite. So this is a contradiction. So A is finite. So far we have considered the notion of compactness in general for any topological space. But what we expect is, well, if we confine ourselves to metric spaces, there should be tools to decide, criteria to decide about whether a given set is compact or not, which might be simpler than just the definition of compactness. Well, in fact, if we confine ourselves further to Euclidean spaces only, well, we might get even simpler criteria for compactness. But in order, that will be the case, but in order to motivate that, let's consider now a few examples in metric spaces and in particular in Euclidean spaces. So we'll continue with examples. So example 3. Now let's consider Rd, and let S be the set of all 1 over n's such that n is a natural number, a positive integer. So this is 0, you have 1, 1/2, 1/3, and so on. So the question is whether this set is compact or not. Now, so far, we only have the definition of compactness. But what you can see is if you have 1 over n plus 1, then you have here 1 over n, and here 1 over n minus 1. Now, if I take an epsilon ball about this distance is larger than this distance, so I can find an epsilon ball about 1 over n, which actually contains 1 over n from this set. Since the distance between 1 over n plus 1 and 1 over n is less than this distance, well, I can just take this as my epsilon. Now, for each n in n, set epsilon n equal to 1 over n minus 1 over n plus 1, which will be n plus 1 minus n, 1 over n times n plus 1. This will be positive. Now consider G equal to the epsilon n ball about 1 over n. Now when we have the usual metric on Rn, well, we can delete the metric part. This is with respect to the usual metric, such that n is in n. Are these open sets? Yes, every epsilon ball is open. So this is a collection of open sets. Does this cover the set cap S? Yes, for each point in the set cap S, there is an epsilon ball where that point is the center of the epsilon ball. Now, G is clearly an open covering of S. Does it have a finite subcovering for S? Now, here, note that for each n in n, we have taken epsilon n such that one has the epsilon n ball about 1 over n intersection S is just 1 over n itself. It does not contain 1 over n plus 1. It does not contain 1 over n minus 1. well, the remaining members of cap S are even further away from that. But then, for any finite non-empty subset E of n, we have that the union of B epsilon n 1 over n and in E, the intersection of this with S is just the set of 1 over n's where n is in E. Because each of these from S only contains 1 over n, and we get this. But this cannot be S because this is finite, S is infinite. So S is not compact with respect to D, the usual metric. But here, is this set closed? It's not. Why? 0 is a cluster point of this set, but 0 does not belong to this set. So what if I take S prime by adding 0 to that? Will that be compact? Well, this will be compact. I will leave fully writing it to you, but we can just sketch the proof on the picture. Now, if you take any open covering G of S prime, the distinction of S prime from S will be such that as 0 is in S prime, there will exist some G alpha which contains 0. But then, since this is a metric space, there will exist an epsilon both about 0, which is actually entirely contained in G alpha. But, so you take that, but what remains from cap S prime on this part, that will be finite. So for each of them, I can take one open set from the open covering, which contains that point. Then I can get a finite subcollection of the open covering script G I started with, which will be a finite subcovering of G for S prime. I advise you going through writing that in full, but this is compact. So here, the non-compactness of this set actually, well, one important reason for that is that this set is not closed. There are points which are arbitrarily close to the set, cluster points, which do not belong to the set. Now, to deal with the coming example, let's have a lemma which we will use later on as well. Now we introduced the notion of boundedness. Now let's consider a metric space now. Let Xm be a metric space. M, a real number which is positive, and A non-empty finite subset of X. The claim is, if I take the cap M balls about points X when X is in A and take their union, this will be bounded. If I take finitely many M balls in this metric space and I take the union of them, is bounded with respect to M. Now, what's the picture here? Now you have, if it's in R2, for example, finitely many points, and you have M balls about them. I can have also this situation. The set is the union of these M balls. Now, for boundedness, there should exist some positive real number, say cap K, since we use cap M here, cap K, such that no matter what 2 points in the union of these epsilon balls I take, the distance between these 2 points will be less than or equal to that cap K, the existence of some such cap K. So here, that actually depends upon how these are distributed, but since there are finitely many, I can take the set of all distances between points x, y in A with respect to M. This will be what? This will be a finite set, since A is finite. So it will be a finite set of real numbers. But then the maximum exists. And let me write that L exists since A is finite. So that will be the maximal distance. Well, I take all points and consider their distances. The farthest away 2 points, well, there exists the farthest away 2 points in this set, and their distance is equal to this maximum. But if, for example, these are the farthest 2 points, well, I can take this point, I can take this point, then the distance between these 2 points would be larger than the farthest distance between points in cap A. But the distance of this to here, well, that's in a cap M ball, will be less than or equal to, in fact, less than cap M. Likewise here, the distance of this to this, that will be less than cap M. So set K equal to 2M plus L. Now, we claim that this K will do the job to conclude that this union is bounded. So take any X, well, I wrote X, so let me write here, take any Y, Y prime in this union. Well, then Y belongs to some such ball. Well, Y prime belongs to some such ball as well. Well, then Y is in Bm cap mx and y prime is in Bm cat m x prime for some x prime in cap A. Now, I wish to show that the distance between these 2 points is less than or equal to this cap K. But I'll use the triangle inequality clearly. Now, m y prime, that's less than or equal to myx plus mxx prime plus mx prime y prime. But what do we know about this? Well, since y is in here, this is less than m. mxx prime, well, xx prime are 2 points in cap A, so it's a member of this set. Well, so that's less than or equal to the maximum cap L. This is less than or equal to cap L. But here, y prime belongs to this cap M ball, so this is less than m. So this is less than or equal to L plus 2m, which is k, thus the union of these finitely many cap M balls about x when x is in the finite set cap A is bounded with respect to m. Now let us consider say R2 itself and check whether R2, the plane, with respect to the usual metric, is compact or not. This is the 4th example. I take R2 together with this usual metric, and I take the set A equal to R2 again. The question is whether this is compact. Well, let me take G as the 1 balls with respect to D. I leave that out about X such that X is in R2. Now we have seen this is an open covering of R2. Well, these are all open sets. These are 1 balls, epsilon balls, they're open. Moreover, for each x in R2, well, there is at least one such that the center is x, so x is in here. So is an open covering of R2. Does that admit a finite subcovering for R2? Well, let us take any finite non-empty subset of R2. Since this is indexed over R2, well, if I take any finite subcollection of this, non-empty finite subcollection of this, well, then this means that I'm taking some finite non-empty subset of R2, and I pick those epsilon balls, the epsilon balls corresponding to points in cap E. But now what do we know about B1x when x is in E. Here M is cap M is 1. Well, this is a finite set, so this is finitely many epsilon balls of the same radius. What do we know about their union? It's bounded. With respect to D. What about R2? Is it bounded? No, no matter what positive real number you give, you can find 2 points, say on the x-axis, whose distance is larger than that. So, union B1x, x in E. This cannot contain R2, as R2 is not bounded. So R2 is not compact. Here, at least one reason of this set with respect to the usual metric being not compact was that this was not closed. Here R2 is closed. It's open and closed simultaneously. But here the reason is that it's not bounded. Well, what does Heine-Borel theorem say about compactness in Euclidean spaces? A set is compact if and only if it's closed and bounded. So, well, this will be our characterization of compactness for Euclidean spaces. Is that true for metric spaces? No, well, we have seen examples of that. Now, for example, if you take the discrete metric, and if you take R2 again, is R2 closed with respect to the discrete metric? Well, everything is closed with respect to the discrete metric, R2 as well. Is it bounded with respect to it? Yes, because the values are 0 or 1. Well, the distance is less than or equal to 1 between all 2 points, but that's not compact. Why? R2 is not compact with respect to the discrete metric since it's infinite. It was only the finite sets which were compact. Okay. But before we go, and at the topological space level, we'll have another characterization. Now, after we are over with the examples, we'll have a 3-level characterization of compactness. But before that, although that will be a simple corollary to Heine-Borel theorem, what I said at the beginning of this course was, we have the algebraic structure of R, we have the order structure of R, but that is not all. That's not the entire story. We need also some topological structure. And for that, we actually said, well, assuming the supremum principle would suffice for that. So it is the supremum principle, actually, which gives the topological structure of R. Now, let's go through the proof of that the closed interval 0, 1 is compact with respect to the usual metric, just using the definition of compactness without resorting to any further refined tools, and the supremum principle. Any questions so far? No. Okay. This is the 5th example, I guess. Is compact with respect to D, which we use for the usual metric. Let's proceed by a contradiction. Suppose not. Now we have just a definition of compactness. Well, then that means there is at least one open covering G of this unit interval such that it has no finite subcovering for this interval. Because if every open covering has some finite subcovering, then this would be compact. Well, then, there is some open covering G of 0, 1 such that G has no finite subcovering for 0, 1. That should lead to a contradiction. Now, I can take any point in this interval x and check the following. Does this script G have a finite subcovering for this interval from 0 to x? Well, since script G is an open covering of the entire interval, it will also be an open covering for this, because the union contains the entire interval, so the union will contain this as well. Well, one possibility is that, there is no x such that G has a finite subcovering for this. Is that possible? Now, if I take x equal to 0, for example, well, 0 belongs to a particular member of this, because G is an open covering of the entire interval. 0 is a point in that interval, thus it must be belonging to some open set in this collection. But if I just take that singleton set, then that will be a finite subcovering for the intervals from 0 to x when x is equal to 0. But that tells more than that. This is a metric space. If 0 is in an open set in here, well, then there must be some epsilon ball about 0, which is entirely contained in that set. So, well, I can in fact go further for some epsilon, and if I take, say, epsilon naught, if I take epsilon over 2 here, this interval, that will belong to a single member of script G. So that will have a finite. So that set will not be empty. But let's first note down what we said so far. Now I'm interested in this set x in 0, 1, such that G has a finite subcovering for 0x. What we know so far is this supposition tells 1 is not in S, but what we have just noted says 0, and in fact, some positive numbers are in here. Okay, let's write that first. Now, since 0 is in this interval, there is some say G0 in script G with 0 is in G0. But then there is some epsilon not positive such that the epsilon naught ball about 0 is contained in G0, since we're in a metric space. So, in particular, if I take 0 up to epsilon naught over 2 and include that, is contained in G0. That is, singleton G0 is a finite subcovering of script G for 0 epsilon naught over 2. Well, let me do it like this, less than 1, so that epsilon naught over 2 is not beyond this. That's not possible, but if there is some epsilon naught, I can take that as small as I wish. Okay. Next. This means what? This is in S. So, S is non-empty. What else do we know about S? Well, it's a subset of 0, 1, so 1 in particular is an upper bound of S. Moreover, one is an upper bound of S. But here we have a non-empty subset of reals which has an upper bound. What do we know about it? By the supremum principle, the supremum of S exists. By the supremum principle, say, well, let me just give a name to that. Sup S exists. So where does X star itself belong? Well, X star in particular is an upper bound of S, being the supremum, and epsilon naught over 2 is an S. Since it's an upper bound, it has to be larger than or equal to that. But it's the supremum and 1 is an upper bound. Thus, it's also less than or equal to 1. That is, X star is in 0, 1. But then, since script G was an open covering of 0, 1, there must be an open set which contains X star in that collection. Thus, there is some G in G with X star belongs to G. Okay, but we're in a metric space, so for some epsilon positive, the epsilon ball about X star, that must be in G. So we have here X star, and we have an epsilon ball about that. And that's contained in G. Okay. This is the supremum. What can we tell about this part? Well, that has to contain at least 1 point from cap S. Because if X star is an upper bound, then this should be, since X star is equal to the supremum of S. Now there exists some, say, Y in S intersection X star minus epsilon X star. This was our very first proposition. Okay? But then what? Since Y is in S, there is a finite subcovering of script G for 0Y. By definition of S, or let me write it like, since Y is in S, there is some finite subcovering, say G1, GK of G for 0Y. So up to this point, I can cover them by finitely many members from script G. But if I add to that G, then I can cover more. Now consider 0. Now here, if I add to X star half of this epsilon, but that might go beyond 1, okay? So let me just take minimum of this and 1. Now, will G1, GK, G, will it cover this interval? Yes, because up to here, you have G1 up to GK, they cover this, but this is contained in G. If I add G to this collection, covers 0, minimum, X star plus epsilon over 2, 1. But is this possible? This is either 1, then this means, well, let me write it in full. If minimum X star plus epsilon over 2, 1 is equal to 1, then G1, GK, G is a finite subcover of G for 0, 1. That contradicts our supposition, because we assumed that it had no, contradicting our supposition. Okay, if this minimum is X star plus epsilon over 2 and 1, X star plus epsilon over 2. If it's this, then Well, since this finite subcovering covers this, well then that would mean x star plus epsilon over 2 is in S. But is that possible? X star is the supremum of S. Contradicting that, x star is equal to the supremum of S. So the supposition must be false, thus 0, 1 is compact. And as you see here, we used just the supremum principle and just the structure of the reals. Well, okay, so let me stop here because we have gone beyond.